Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127 Random Signals. In this lecturette, I'm going to show you how to use the R statistical software package to perform statistical inferences. Specifically, I'm going to show you how to perform estimation of population mean in R, and I'm also going to show you how to perform two types of hypothesis testings in R, and those are the lower tail tests and the upper tail tests. And I'm also going to define what we mean by lower tail tests and the upper tail tests. Please note that for your final exam, I will not be asking you to perform statistical analysis using pencil and paper. Instead, I'll be asking you to perform all kinds of analysis using the R software, and you're going to give me a reasonable conclusion based upon your statistical analysis in R. For now, let's start our discussion on performing estimation of a population parameter in R. If you recall from the previous lecturette, the goal of statistical estimation is to derive a confidence interval which will contain the population mean with high degree chances or with large probability. Specifically, we use a sample from the population, and the goal is to obtain a confidence interval such that 1 minus alpha percent of such intervals from the other samples are expected to contain the estimate of the population mean. And this confidence interval is obtained using this simple formula here. C of I is equal to x bar plus minus t of n minus 1 comma 1 minus alpha over 2 times s over square root of n. The term x bar is the sample mean, the term s is the sample standard deviation, and n is the size of the sample. To obtain this parameter, this t parameter, which is the percentile, we use the R function qt in this manner. Qt, it takes the first argument as 1 minus alpha over 2, and the second argument is the number of degrees of freedom. Let's apply this in R for this particular example here. Let's say that a factory produces several light bulbs, and we are trying to find out what is the average lifetime of such bulbs. Specifically, we are trying to find out the range of values that are going to contain the average lifetime of the bulbs that this factory will ever or has ever produced. So in order to do that, we cannot take the entire population, obviously, because it is not easy to obtain the entire population. This factory may have sold, let's say, millions of bulbs. It simply doesn't make sense to monitor the individual lifetimes of all of those bulbs. Instead, we rely on a sample from that population, which is a subset of that population. Specifically, in this case, we are extracting a sample of 30 light bulbs. Let's say that further, this sample has an average lifetime of 9,900 hours, and the sample standard deviation is 125 hours. At 0.05 level significance, or 0.05 significance level, we need to derive the confidence interval such that it is going to have the 95% chance that it is going to contain the true average lifetime of these bulbs. So let's start our analysis in R. Okay, so I tend to use my Linux operating system to perform my analysis in R, but your analysis or the functions that we are going to use in this lecturette are still going to apply for other operating systems like Windows and Mac OS X. Okay, so let's open R. So that's my R, and if you carefully observe here, it's quite similar to other interpreted languages like Python or MATLAB, and we can enter our commands here and to find out whether or not our commands work properly. And once we are sure that our commands work, we can later also put them in a nice script file, which we can just execute for different kinds of data. So let's perform the confidence interval estimation for the preceding example. In the preceding example, from the sample, I have the value of x bar as 9,900 hours. I have sample standard deviation as 125 hours. The size of the sample was equal to 30 light bulbs. And we need to derive the confidence interval. This confidence interval is going to have 2 points, the upper limit and the lower limit. Let's say that C upper limit is x bar plus the t percentile times s over square root of n. Before I evaluate Ci upper, let me obtain the t percentile. So t percentile is qt 1 minus alpha, which is 0.05 over 2, comma 30 minus 1. So that's the formula that I'm applying here. QT1 minus alpha divided by 2, comma n minus 1. That's the formula that I applied. So the value of t perk here is equal to 2.045. So I can obtain the upper limit as x bar plus t perk times s divided by square root of n. So if you're familiar with MATLAB, some of the functions that you typically use in MATLAB can still be applied to R somehow. I mean, the common functions have the same function names. For example, square root is sqrt. So that's the upper limit. The lower limit will be x bar minus t perk and the remaining formula. So C lower is that. So CI upper value is 9946 and C lower value is 9853. Okay, so for this particular problem, the 95% confidence interval is 9,853 hours to 9,947 hours. So this interval has 95% chance of containing the true average lifetime of the bulbs. Now, using this confidence interval, I can answer some other interesting questions as well. For example, if I were to ask these factory guys, hey, you know what, is 10,000 hours a valid estimate for the lifetime of the bulb? Now, the 10,000 hours, is it likely? That's my question. Now, since 10,000 hours is not present inside of this 95% confidence interval, it is not a likely value. No, it is not likely because 10,000 hours is not contained in the 95% confidence interval. So you can answer such interesting questions by performing estimation of the confidence interval for a population parameter. Let's move on and discuss what hypothesis testing is. In my previous lecturette, I introduced you to the pencil and paper format of hypothesis testing. Now, the goal of the hypothesis testing is to find out whether a hypothesized value of a population parameter is likely or not. So the goal here formally is sometimes we hypothesize a value of a population parameter, let's say mean, and we would like to check whether it is a likely estimate or not. In order to perform this hypothesis testing, there are a series of algorithmic steps that one needs to perform. The very first step is to actually define the null hypothesis, which is essentially the hypothesized value of the population parameter is true. That happens to be your null hypothesis. The alternate hypothesis, however, is anything but the null hypothesis. For example, an alternate hypothesis will be this is not the likely estimate, or the likely estimate is less than my true population's mean, or it is greater than the true population's mean. So these are the two statements that one defines. The null hypothesis, which is a statement that the hypothesized value is true, and the alternative hypothesis, which is anything but the null hypothesis. Next, we specify a significance level called alpha. Now, this alpha is the probability of incorrectly rejecting the null hypothesis. We will go into the arena of null hypothesis with an inclination to reject the null hypothesis, and we would like to find out whether or not we are making a grave mistake in rejecting the null hypothesis. Alpha happens to be that threshold error for incorrectly rejecting the null hypothesis, meaning that in this test, I cannot tolerate more than alpha percent error in incorrectly rejecting the null hypothesis. Consequently, we would want this value to be very small. For example, 5% is a reasonable choice for the value of alpha. If alpha is equal to 5% or 0.05, then that means if I were to reject the null hypothesis, there is 5% chance that I am wrong. Next, using the sample's parameters, namely the sample mean and the sample standard deviation and the size of the sample, we compute something called as the test statistic and associate a probability value with it. We associate a probability value with this computed test statistic. Now, this probability value gives you the true probability of incorrectly rejecting the null hypothesis. I would like for this probability to be smaller than the alpha that I originally specified. I would like this value, this probability value, to be smaller than the threshold that I have defined originally. If this probability happens to be smaller than alpha, then I can safely reject the null hypothesis. Otherwise, I will not reject the null hypothesis. So these are the algorithmic steps which become much more clear once we actually see an example. So let's take an example which pertains to the problem that we have already discussed in my previous slides. So suppose the manufacturer claims that the mean lifetime of light bulb is more than 10,000 hours. In a sample of 30 light bulbs, it was found that they only lasted 9,900 hours, and the sample standard deviation is the same, 125 hours, and the significance level is 0.05. Can we reject the claim made by the manufacturer? Let me show you how you will perform those series of steps in R. The very first step is to define the null hypothesis. You will not perform a statement like this in R, but rather this kind of a statement will be in your page using a pencil. So we define the null hypothesis. So the null hypothesis in this case is that the true mean is actually equal to 10,000 hours as claimed by the manufacturer. The alternate hypothesis is anything but the null hypothesis. In this case, we say that no, you know what? The mean lifetime of the bulbs is not 10,000 hours. In fact, it is less than 10,000 hours. Because we have a statement that goes something like this, mu is less than 10,000 hours, therefore this is called as a lower tailed t-test. Because our alternate hypothesis has this less than symbol in its definition. So these are my null and alternate hypothesis. So null hypothesis is the true mean is equal to 10,000 hours as claimed by the manufacturer, whereas the alternate hypothesis is no, the true mean is less than 10,000 hours. Using the sample parameters x bar and standard deviation and the size of the sample, we evaluate the t statistics. So if we perform x bar minus mu or s over square root of n, we should get the value of t as negative 4.38. By the way, mu is the hypothesized value, which is 10,000. So if I were to apply this formula in R, I should get this value, negative 4.38, and then I'm going to obtain the probability value associated with this obtained statistic. And depending on the value of that probability, whether it is greater than alpha or less than alpha, I'm going to either accept this null hypothesis or I will fail to reject this null hypothesis. Let me put this in action in R. So first things first, using pencil and paper, you may have written your null hypothesis and the alternate hypothesis. Next, we need to obtain the t statistic. So t stat, let me call it t stat, is equal to x bar. You know what, let me reset the values of x bar and all. So x bar is 9,900. Mu, the hypothesized value is 10,000. Standard deviation is 125. Alpha is equal to 0.05. And I need to get the t-stat as x bar minus mu over sigma s over square root of n. So s over square root of n. So the value of t-stat is indeed negative 4.38. With this evaluated t-stat, I need to find the probability of incorrectly rejecting h naught. And I can do that using the pt function in R. So pt, the value of the t-stat, comma, the degrees of freedom is 30 minus 1, or rather n minus 1, where n has been set to 30 already. So I will evaluate this, and this is the probability. The probability is 7.03 times e to the negative 5. So that's the probability of incorrectly rejecting h naught. So if I were to reject the h naught, that the mean is equal to 10,000, the chances that I'm wrong is this much right here. Infinitesimally small chance that I'm wrong. So I will go back to my slides here and perform this analysis. So because I got the probability value, p-val, as a very small value, which is 7.03 e to the negative 5, the probability that I erroneously reject the null hypothesis is really very small. So I will make my conclusion based on this particular p-value. Because this p-value is really small, it's even smaller than alpha, I can safely reject h naught. So in this case, I'll safely reject h naught and obtain my analysis like this. There is sufficient evidence to suggest that true mean is less than 10,000. Because I'm rejecting the null hypothesis, I'm going with the alternate hypothesis now. So I go with the alternate hypothesis. So that's an example of a lower tails test. It is called as a lower tail test because of the shape of your alternate hypothesis. In this case, this mu is less than, it is lower than 10,000, and therefore I'm going to use my lower tails test. Let me show you an example of an upper tails test of unknown variance. Now, all the examples that we have seen so far, we are assuming that we do not know the variance of the entire population. This assumption helps us to use the student's t distribution. Let's take a look at the upper tail test. Suppose that the food label on a cookie bag states that there's at most 2 grams of saturated fat in a single cookie. We want to analyze this. We want to find out, or we need to perform this hypothesis testing. So we obtain a sample of 35 cookies, and it is found that the mean is in fact 2.1 grams. Assuming that the sample standard deviation is 0.3, at 0.05 significance level, can we reject this claim? We will perform the same set of analysis that we have performed previously, just that now our test type is going to be an upper tail test, and I'm going to show you how. First things first, we need to define our null hypothesis. So first we are going to define, first we are going to define the null hypothesis, which is the hypothesized value of the population mean is true. So my null hypothesis is average saturated fat is indeed equal to 2 grams. So that's my null hypothesis. The alternate hypothesis is anything but the null hypothesis. In this case, it is true average saturated fat is greater than 2 grams. Because we are using this greater than symbol, it is the upper tail test. So it is upper tail. Using the similar principles as the lower tail test, we are going to obtain the t statistic, which is x bar minus mu, or s over square root of n. And then with this, we are going to associate a p-value, and we are going to obtain it in R using the pt function. So whatever statistics we evaluate, we pass it as the first argument. The next argument is the degrees of freedom, which is n minus 1, one value or one less than the sample size. I need to include this additional parameter here. Lower dot tail is equal to false because I'm trying to perform an upper tail test. So let me put this in action in R. So let's put this in action in R, and let me quickly change my display. Okay. In this case, the value of X bar is equal to 2 because that's the value from the sample of 35 cookies. So this is the sample mean of 35 cookies. Then I have S as, oh, you know what? The sample gave me 2.1. Let me fix this one more time. X bar is 2.1. S from the sample is 0.3. So that is sample standard deviation, and N, the number of cookies, is equal to 35. The hypothesized value of the saturated fat amount is equal to 2 grams as claimed by the manufacturer. So mu is equal to 2. So I need to evaluate the T statistic. So let me just call it T here. So X bar minus mu over S over square root of N. So the value of T is 1.97. So that's the value of T. Next, I'm going to evaluate the probability value associated with the statistic. The probability value that I'll get will be the probability of incorrectly rejecting H naught. That is the probability that, hey, you know what, even if I were to reject H naught, the chances are that I'm wrong is equal to that probability that I'm going to evaluate next. So P while is equal to PT. First argument is the T statistic. Next argument is the size of the sample minus 1. And the next parameter is lower dot tail is false because I'm performing an upper tail test. So the p-val is equal to 0.028, which is less than the specified threshold for the error of rejection, of incorrectly rejecting H naught, and that was 0.05. So in this case, it's telling me that I have 2% chance of incorrectly rejecting H naught. So if I reject H naught, the chances that I am wrong is only 2%. So I can safely reject H naught. So I can simply reject H naught. So going back to my slide, now based on this p-value, here's how I'm going to summarize my result. Here's how I'm going to summarize my result. Because p-value is equal to 2%, which is less than 5%, the probability of incorrectly rejecting H naught is below the threshold, which is alpha. Therefore, I will reject the null hypothesis and conclude that the true average saturated fat is greater than 2 grams. So I'm going with the alternate hypothesis H of A. So that's your upper tailed test. So in this lecturette, I showed you how to use the R software to perform estimation, how to perform hypothesis testing, namely the lower tail test and the upper tail test. Please pay careful attention when to use an upper tail test and when to use the lower tail test. For your in-class participation problem, here's what I would like for you guys to do by Friday 5 p.m. and this is going to be in the form of a text box entry where you're going to give me the T statistics value, the probability value, and your valid conclusion in proper words. So a professor assesses marks of 9 students in his class, so that's the sample size, and finds that the sample mean is 520 and sample standard deviation is 50. The average score of the previous class was 600. Is the professor correct to conclude that the marks on average has gotten worse? So 600 can be construed as, in quotes, the population mean. So this is the hypothesized population value, and you need to find out whether this hypothesized value is correct or not using an appropriate type of hypothesis testing. You have to decide whether you should be using a lower tailed test here or an upper tailed test here. So for Friday's in-class participation, you're going to give me the t statistic using x bar minus mu over s over square root of n. You're going to give me the p-value, and you're going to give me a conclusion in proper statistical English, which is something like that right here. So this is a proper statistical English in which I summarize my findings using the statistics. Okay, I think it's a good time to stop this lecturette right here. I do not want this lecturette to get overly long. In my next lecturette, I'm going to show you a real data, and we are going to perform some analysis using the real data. Specifically, we'll be focusing on hypothesis testing, where we'll be comparing two different samples, or rather we'll be comparing two different populations. Okay, I think it's a good time to stop this lecturette right here.